split into two parts. How in octahedral it will split, I will show you. So first write a point with me. Thus, in octahedral complexes, the 5d orbitals splits up into two sets. As I told you, when they will feel repulsion, it will split into two parts. One is your EG orbital. One is your EG orbitals, and now wait a minute. Split into two sets. Two sets. One set consisting of two orbitals. One set consisting of two orbitals. That is your dx square minus y square and dz square. I told you there are 5 orbitals of d subset, in which dx square minus y square, dz square, dxy, dyz, dxz, all of this of higher energy. This will have higher energy, and this is also known as EG orbitals. EG orbitals and other set consisting of three orbitals. And that why remaining three. That is why remaining three. Dxy, dyz, dxz. These are the three orbitals of lower energy. And this is known as T2G orbitals. Please to write. Let me know when you are done with this.
Done.
Very good. Now see what will happen here. I'm just going to. You need to draw this first. I'm going to explain this. Just wait a minute. Don't write right now. See, this is your free matter when d orbitals, that means dxy, dyz, dxz, dz square, dx square minus y square, all are having same energy. Now, when ligand is going to approach central metal atom, what will happen? Repulsion will take place, so energy increases. Now, when the bonding will take place, actually, so these orbitals, this is free metal ion, then average energy of d orbitals in a spherical crystal field. Now, what will happen when the repulsion will be more? For coordination number 6, we are studying what will happen. A splitting of d orbital will take place. A splitting of d orbital will take place. So for coordination number 6, octahedral complexes, this orbital is split into two parts. One is called EG orbital and another is called T2G orbital. In EG orbitals, you have two orbitals, that is your dx square minus y square and dz square, which will have higher energy and another three orbital will be together, and this is your dxy dyz dxz, and it will have lower energy than this dx square minus eg orbitals. This t2g orbital will have lower energy than this eg orbital. This is your barycenter, just like your reference point. It is lower than this, the energy is lesser. Greater than this, the energy is more. And this delta naught is your basically crystal field stabilizing energy. What we can write for delta, this delta naught is your crystal field splitting energy, CFSE. Now you can make it very important. It is how to calculate delta naught. I will tell you. Very easy it is. Let me know when you are done with this.
Done, sir.
Very good. Austin, are you done with this?
Done, sir.
Okay, so this CFSE is very important, crystal field stabilizing energy for what do we say? For octahedral. Let's say if you have D4, that means in d orbital, if you have 4 electrons. So this is, just wait a minute. No, before that, you know that a strong field ligand pairing up will take place and weak field ligand pairing will not take place. So I'm going to make a list, electronic configuration. You know that first electron will start filling in which orbital? You know that basically this is your d orbitals together, all of them together. Now what happens after this? Splitting took place. Now this is your 3 orbitals and above it is 2 orbitals. So this is lower energy level. So if you got D3, let's say D4 or D3, so in which orbitals, T2G or EG, in which orbital electrons will go first, EG or T2G? Both of you. If you are going to fill the electron in which orbital, this is basically a bow principle. In which orbital you are going to fill the electron first, EG or T2G?
Easy.
A bow principle says that orbital you are going to fill first, which is having lower energy. So 1, 2, 3. Are you getting my point?
Yes.
So it will go in T2G first and then EG. Now see, number of electron I'm going to give here, number of electron. Look at this, focused, please be focused. And here, if the ligand is a strong field ligands, that means electrons will pair up, electron will pair up. And if weak field ligand, electrons won't pair up. This is what we have studied, yes or no?
Yes.
Now, if you have 1 electron, so you cannot pair up. First, it will go in T2G1, EG0, whether it is a strong field ligand or weak field ligand. Are you getting my point? First, you
Yes.
need to fill in the lower energy. If you have 2 electrons, so Hund's rule says that you need to fill singly first. So T2G2 and then EG0. Again, this will be also same. T2G2, EG0. Now the third one, again, it will be same. T2G3, EG0. It will be also same. T2G3, EG0. Now comes fourth electron. If 4 electron comes, see, this is the scenario. This is your T2G and this is your EG. Sorry, this is your T2G and this is your Eg, right? Now, what will happen? First electron will go, second electron will go, third electron will go. If it is a strong field ligand, start pairing it up. Don't go into this. You are going to pair it up. And if it is weak field ligand, then what will happen? This is your Eg and this is your T2G. So first, what you need to do? First, 1, 2, 3, and then fourth. In this, pairing will not take place. So according to that, this will be T2G4 because a strong field ligand, and this is your Eg0. And here it will be T2G3 Eg1. Are you getting my point?
Yes.
First, right up to this. We will do up to 10 electron.
Done.
Done, both of you. Now you are going to do by on its own. I'm going to give you. This is your fourth electron, and then 5, 6, 7, 8, 9, 10. Up to this, you are going to do it. If you will not be able to do it, just let me know. Austin, you need to singly filled all of them. 5 orbitals singly filled. See, 5 electrons are there. So just imagine that this is your for a strong field ligand. 2 orbitals above and 3 orbitals below. So 5 electron you have. So first, second, third, fourth electron you are not going to give into this because this is a strong field ligand. So 4 and then 5. So this is your T2G as you know that, and this is your EG. So what will be the configuration? T2G5 EG0. But for weak field ligand, you can see this is your EG and this is your T2G. So weak field ligand 1, 2, 3, and then stop. Then think about this is weak field ligand, so pairing will not take place. 4 and then 5. So this will have configuration T2G3 EG2. Are you getting my point? Yes or no?
Yes, sir.
Yeah.
Now again, if you have 6 electron, so 1, 2, 3, 4, 5, and then again you are going to pair it up, so it becomes 6. So it will be T2G6 EG0, EG0. If it is weak field ligand, already you have filled 5 electron, 6th electron. Now there is no space. Now it will start pairing up. So it will have T2G4 EG2. Are you getting my point?
Yes.
Are you done with this? Now, if you are
Yes.
going for this, it becomes after filling this all, now electron will start going to that T2G6 and then EG1. And for this, uh, you need to think 4 and now it becomes T2G5 EG2. Now come to this 8 electron T2G6 already filled T2G EG2. Now for this T2G6 EG3 and then T2G6 EG4. Now come to this after T2G5, that means this, and now T2G6 EG3, T2G6 EG4. Oh, wait a minute. T2G5. Wait a minute. There is a mistake. 8 electrons. If we have 8 electrons, what we need to do? 8 electrons. So this is your orbital and this is your T2G, above is EG. So 8 electrons, 1, 2, 3, no pairing, 5, 6. Now I start pairing. 5, 6, 7, 8. So it becomes T2G6 Eg2. Then comes your T2G6 Eg3 and T2G6 Eg4. Is that clear, both of you?
Yes.
Please do write it. Please attempt the assessment test, assessment after just after the class. Do you attempt it?
Yes, sir.
Okay. What about you, Humam?
Yes.
Okay. Let me know when you are done with this. So in VVT, we came to know some of the ligands. They act as a strong field ligand and weak field ligand. That complex you have to keep it in mind. And I will give you a spectrochemical series in which the ligand's strength is compared, which one will be the most strong, then least, like this. Okay. Done with this, both of you? Mom.
Yeah, yes.
Okay. Now see, CFSC, there is a formula for CFSC. Crystal field stabilizing energy has a formula that is equal to minus 2 by 5 minus 2 by 5 n into T2g electron n into T2g. Oh, just wait a minute. N T2g like this plus 3 by 5 plus 3 by 5 n Eg electron into delta naught. Where from where it comes to 3 by 5 and 2 by 5. So you can see 3 by 5 that is for Eg and 2 by 5 delta naught that is for T2g, and there will be negative sign in Eg 2 by 5. 2 by 5 that means what? If you are going to divide it, you will get 0.4. So formula can be this formula can be also written as this formula can be also written as minus 0.4 into n T2g. What is n? N is the number of electron in T2g orbital, plus we can write 0.6 NEG. NEG means number of electron in EG orbital into delta naught. Now, how will you know whether how many electron is present in this or that? So very simple. I'm going to write n T2g. That means number of electron in T2g, number of electrons in T2g, and NEG, that means number of electron in EG, number of electrons in EG. Are you getting my point? Now, how will you know? Let's say if a complex is given and D in which we saw the configuration of D, if D4 is given and in the question, or you can either recognize it by the ligand, if it is low spin that is given in the question. Low spin that means pairing will take place. Low spin pairing, high spin no pairing. Low spin pairing because when an electron gets paired, spin will be lesser. So that means this is your, you can see this is your EG and this is your T2g. This is your T2g. So how many electron in the in d orbital? 4 electron. So how you are going to do? 1, 2, 3. Since it is low spin, that means a strong field ligand is there. That means pairing will take place. So the fourth electron will not go into this, but into this. Now, how you are going to calculate CFSE? Very simple. CFSE will be equal to minus 0.4 into number of electron into T2g. How many electron is present? 4 electron is present, plus 0.6 into how many number of electron present in EG? That is 0 and square bracket delta naught. Now you can see that this whole part, since it is 0, it becomes 0, but 0.4 into 4, that becomes minus 1.6. 6 into 4 into 4.4, 1.6 delta naught. So for this complex, CFSC crystal field stabilizing energy will be minus 1.6 delta naught. Is that clear?
Yes.
Please do write it. Let me know when you are done with this. Are you done with this?
Yes.
Okay. Now see, if pairing energy is given, then what happens? P for pairing energy. If delta naught, as you know that this is your CFSE, crystal field destabilizing energy, greater than pairing energy. If it is greater than pairing energy, then D2sp3, D2sp3, that means low spin. Then that means low spin, that means pairing will take place, low spin complex. And if crystal field destabilizing energy lesser than pairing energy, this is the minimum energy for which it will start pairing up. sp3d2, sp3d2, that means high spin complex, high spin complex. Are you getting my point? P is for pairing energy, and delta naught is your CFSE of octahedral, or CFSE for octahedral complex. I think it's clear to both of you. Please do write this. And there is one question then that I'm going to raise. First, write it. Let me know when you are done with this. Are you done with this?
Yes.
Okay. Now, why it is so that this x square y square goes up and dxy dyz dxz comes down? Are you getting my point? Why it is so? Three orbitals goes down in octahedral and two orbital goes up, higher energy or lower energy. Why it is so? So this answer lies here. As you know that all the orbital dxy, dyz and dxz, all the orbitals is in between the axis, except this and this, all the orbital exist between the axis. Yes or no, Humam and Austin?
Yes.
And you know, in octahedral complexes, the ligand approaches between the axis, along the axis, between the axis, the ligand approaches. Wait a minute. On the axis, not between the axis. In octahedral complexes, the ligand approaches along on the axis. And as you can see, only two orbitals are present on the axis. This is your dx square minus y square, and this is your dz square. So what happens here? This will feel more repulsion because the lobes of this orbital is on the axis. And if ligand is directly coming from this side, so it will feel more repulsion as compared to dxy dyz, because the ligand is coming from this side and the lobe is here, so electron is also here, so it will feel less repulsion, so less energy, and this will feel more repulsion because the ligand is approaching on the axis. Are you getting my point, both of you?
Yes.
So if someone will ask you, or if the examiner ask you, why dx square minus y square or d and dz square is higher in energy as compared to these three orbitals, because in octahedral complexes the ligand approaches on the axis. Got it? And this will be exactly opposite in tetrahedral, because in tetrahedral the ligand approaches between the axis, and if between the axis, if it will uh, approach, what will happen? You know that what will happen? uh, the dxy dyz dxz, they will feel more repulsion, so it becomes more energetic, higher energy, because their lobes present in between axis. Are you getting my point, both of you?
Yes.
So here I'm going to start splitting in tetrahedral complex. In tetrahedral complex. So write with me. You can write this here. Ligands approach in between axes. So dxy, dyz, dxz, energy increases due to more repulsion. And energy of dx square, y square, and dz square decreases because it is on the axis and the ligand is approaching now between the axes. Are you done with this? Austin, Humam, are you done with this?
Yes.
Okay. Now we are going to see its splitting as well. So as you can see, the ligands in this tetrahedral approaching between the axis. So this will feel more repulsion. So this will be like this, and 2 by 5 delta T. That means crystal field destabilizing energy for tetrahedral, and this will come in between. So you can write like this, or you can make at the place of this like d orbitals, 5d orbitals. You have dxy, dyz, then this, then this. Please do it. Yeah, let me know when you're done with this.
Done.
Okay. So also you can write CFSE for this in the same way that we did for that octahedral. So CFSE for tetrahedral complexes will be equal to what it will be 0.6 negative because it is downward, and Ne here in the previous one we call it T2G and EG, and here we call it T2 and E. Are you getting my point? Yes or no?
Yes.
And then comes your plus 0.4 N T2, Ne and T2 and delta T. You know that Ne, that means number of electron in A orbitals, number of electrons in E orbital of delta T, and NT2, that means number of electron in T2 orbitals, number of electrons in T2 orbitals. So you can easily calculate it and do the pairing if needed. Are you done with this?
Yes.
Okay, so now I'm going to give you application of crystal field theory. Application of crystal field theory. So the first application is to predict the geometry. Write with me, geometry, that the compound is either inner orbitals, that means low spin inner orbital, or outer orbital, outer orbital. Now what is this inner orbital? That means D2sp3, D2sp3. and outer orbital, that means sp3d2. Now the next one, to calculate magnitude of paramagnetism. To calculate magnitude of paramagnetism. And the third one is to show color property. Color property. If, always remember this, if D1 to D9, that means D1, D2, D3, D4, D5, D6, D7, D8, D9, then there will be DD transition and then there will be colored compound. DD transition occurs. That means there will be colored compound. And for D0 or D10, D0 and D10, colorless. Let me know when you are done with this. Let me know when you are done with this.
Done, sir.
Very good. Please do this question. Any answer? Any answer? Austin, Humam?
Also,
No. Okay, see. First of all, this is your octahedral complex. So I had given this formula for octahedral complex. This formula minus 0.4 n T2G plus 0.6 n EG into delta naught. So here I'm going to write this formula again. CFSC we need to calculate, that will be equal to minus 0.4 n T2G plus 0.6 n EG, and this will be delta naught octahedral. Okay. Now D4, and it is high spin, low spin is pairing. So high spin is not pairing, simple. So you have this T2G, EG, and this is your T2G. So if this is your T2G, now if pairing is not taking place, 1, 2, 3, and then 4 electron, pairing is not taking place. Sorry, pairing not taking place, why I paired it? If pairing not taking place, that means high spin. So the next electron will come into this. Now you can see this will be equal to minus 0.4 into number of electron in T2G orbital, that is equal to 3 plus 0.6 into number of electron into EG orbital, that is equal to 1 into